All right, this is homework 2, part A, question 2, where we are asked to express the heat diffusion equation from part A1 that we found as an algebraic equation via backwards differencing. So just reference again, we found that the change in temperature over the change in time equals the thermal diffusivity, which this is constant, we explained why that was in the last one, times d squared times big T all over dx squared. So to kind of help us later on when we go to actually try to simulate this in a real life code, which the later questions do ask us to divide it into 100 sections, I'm gonna kind of, to help me also with explaining this as a algebraic equation, I'm gonna do some quick nomenclature explanation. So basically, if we have a bar here and we split it up into a bunch of sections, right? So we have this many sections, we have like 1, 2, 3, 4, dot, dot, all the way until n. Each one of these little sections is going to be the change in x, and then any one of these positions or each one of these boxes or these sections is going to be j. So then when we're looking at it here, we have our temperature, right? And so we have what position it will be and at what time. So essentially this can help us kind of be able to understand that, for instance, we're going to have the time equaling the change in time, or basically step size in time, times just a counter in time, or in this case n, because n is going to be the counter of how many, where in the counter of the bar we're at when it relates to time, and then j will be essentially the position, because that's going to be x, which is equal to the change in x times j, which again, this is essentially just saying that we have the size of our bricks, like we said, like the brick size of the section, that will be multiplied by how many bricks we are into the metal bar. So that's what T and X are. That's what they equal over here. So to take the heat diffusion equation that we had found in the first question and express it as an algebraic relation, we can essentially be able to go and do this. So you see we have that there. Let's say we have, this is the left-hand side. I'm going to work on the left-hand side first. So we have dt, that's the change in temperature. So we're looking across the temperature of that bar. So we essentially can be able to say, we're going to have, a change in time, because remember we said that we're looking at the difference in time, or the difference in time, aka the change in time, aka the step size in time is what we're calling this specifically, because time is technically the step size in time multiplied by a counter in time. We can then essentially be able to then look at the difference in temperatures, where we will look at a temperature at some counter plus 1, j, minus just the counter of time j at that current position. So this is still at some position, so let's say it's like the n position along this bar. We're looking at, from whatever counter in time, whatever time point that we're into looking at this bar, we're looking at the temperature at that specific position at that specific time, and then we'll be subtracting that from that same temperature at that same position, but at that time plus 1. So essentially the time a little bit further along, but still the same temperature at the same position at the same place of the bar. So now we have the right-hand side kind of understood, because again, we're looking at the difference in time over difference in temperature over the difference of time. We have that expressed now in an algebraic sense. We can then look at that right-hand side. So I keep reading that name, thermal diffusivity. I'm gonna get it one day. That stays constant, so that can just stay there. And then we also can then break down that d squared t over dx squared. So we can essentially, we would apply the same logic, because again, we're looking at the difference in the temperature. right? So if we're looking at the difference in the temperature, we could then be able, and specifically, we want to look at that across a few different positions. So say we're looking at like position 4, we would want to look at that temperature at that position at that current counted time plus 1 in time and minus 1 in time. So therefore we could then be able to then do this, where we have our change of x, or again, the size of the brick over position forward at that same time that we're looking at the bar, minus at that. Sorry about that, my computer turned off because my computer's old as crap. Anyway, so like I was explaining, we're already over here where we have, again, when we're looking at this specific position of the bar at that temperature, at that amount of time into the bar that we're looking at the temperature, we will then want to look at one position in front of that at that time, and then we'll want to, on this side, look at that position at that same time back, or one to its left. So if this is to its, if we're looking at position 3, if this is to its right, in this case position 4, then this is going to be looking at its position to the left, aka position 2. So then this will be subtracted at that current time as well, minus 1. And then all of that's just going to be over change in x, because again, we had dx squared over here. So from here, we can then simplify this down further, because now we have this written in algebraic equation, but I want to look at this via backwards differencing. So because of that, we then can move some things around. The first things we can do is we can actually get rid of this full fraction, because I don't like it. I don't like fractions. I'm not a fraction person. So we're going to get rid of that. So we can essentially, because we have 2 here and then we have this in the same denominator, we can just pull this whole thing out and then put this underneath the alpha, or that term is alpha. That's thermal diffusivity. We can technically make this change in x squared. And then from there, we can then go and, well, we want to get, in this case, I want to see, we're looking to try to get backwards explicit differencing. So I'm really just trying to get this one here, because this one is going to be helping me achieve that. So we'll want to single this one out. So we're going to need to get rid of everything on this side that's not the TJN plus 1. So to do that, you multiply that over to this side, so then it's going to be the case that then it'll be alpha times that change in t over change in x squared, and then we'll add this TJN over to the right side, so that way then the only thing we have left at that point would then also be to make sure we take care of this one over here as well, because I'm trying to get rid of that fraction. So this one will simplify down to a compounded thing. I can't remember the name of the math way, but we're basically just combining those two together. I can't remember the word right now. It's slipping my mind. I'm still trying to make sure my computer's not about to shut off, so bear with me, please. But anyway, so let me go and write this out now. So we have Tn1j is equal to Tjn, and that's multiplied by alpha change in t over change in x squared. And then we do this, essentially that's a negative, that will apply to that, so then this becomes negative, that becomes positive. Those two can get, I don't want to say added together, but it becomes negative 2 TJN, and then we'll essentially have it over here where we have TNJ plus 1 minus 2 TJN plus TJ minus 1N. So TJ plus 1N minus 2 TGN plus Tj minus 1 n. And there we go. There we have it. Now we have the heat diffusion equation from part A, question 1, expressed as an algebraic equation, now via backwards differencing, because this would help us be able to then figure out backwards differencing for that.